All right, guys, so what we're going to do in this video is we went over all the alcohol, we went over all the ether, and we went over all the epoxide reactions in great detail. We went over their mechanisms, spent a lot of time on them. So now what we're going to do in this video is we're going to go ahead and do a lot of practice problems. So what we're going to do is we're going to try to see how good your mind is in remembering all these reactions. And we're going to do single-step reactions, and over at the end, we're going to do some really hard synthesis multi-step reactions to kind of put it all together. All right, so this is the best way to be able to learn this. All right, so first off, if you remember, what we're going to do is we're going to try to be able to predict the product or predict the reagents or predict the reactant. So first in this one, we have to predict the product. So if you remember, if we have a tertiary alcohol, and that tertiary alcohol is reacting with hydronium and tetrahydrofuran, what was the overall product? Well, if you remember, this was a good elimination reaction. And what does elimination reactions produce? Elimination reactions will remove this whole OH group, right, as water and form a double bond. But where will the double bond form? Will it form there, or will it form over between here? Well, remember, you'd have 3 hydrogens over here, 2 hydrogens over here. We want to follow Zaitsev's rule, so we want it to take from there. And we're going to get this structure. All right, so that would be the answer for this one. All right, next one. We have an alcohol. We have a product. We have to guess the reagent now. All right, well, I got an alcohol and I turned it into an ether. Oh, wasn't that the Williamson ether synthesis? It was. So what did you need for a Williamson ether synthesis? You need sodium hydride, because that will remove that hydrogen ion, and then you have to add on an alkyl halide that kind of has this with the bromine at the end. So what I'd have 1, 2, 3, 4. So let me draw that. 1, 2, 3, 4. And then I'd have my benzene right there, like that. So 1, 2, 3, 4. Whoops, 1, 2, 3, 4, yep. And then right down here, I'd have my bromine. Okay, so here's my alkyl halide that I'm attaching on to this oxygen after I deprotonate it with the sodium hydride. Okay? Next thing, I have to guess the reactant. Okay, well, what do I have over here? I have an alcohol, I have an ether, I have some halogens. I don't even know what the heck happened. Okay, well, I gotta look at the reagents now. All right, the reagents. I got a CF3CO2, a mercury. Okay, so that was like the mercuric acetate reaction. I got a CH3CH2OH. Oh, that's what we added on in the reaction. And then I got an NABH4 to be able to remove the mercuric acetate. So what do I need to look for? I need to look for this because in the mechanism we went over, we added on a OCH2CH3. Where did I add that? Oh, I added it right there. And what did we need for this reaction to occur? We needed a double bond. So if you remember from the reaction, we had to start with a double bond. So where would the double bond have been? Right there. Okay. And the reason why is because you have 1 hydrogen here and you'd have 3 hydrogens over here. You want the double bond to start there according to Markovnikov's rule, right? So this is what we would get like this. We get the Cl there. And then it would come down to the OH, and then we would have a double bond right there, and then like this. Okay, so that would be the result of this reaction. So you're starting with an alkene, and you're forming a ether. Okay, so this is one of the ether synthesis reactions, using an alkene. All right, what about this one? We have an epoxide, and we turned it into a 1,2-diol. Well, I had 3 reactions. One was the binary acid, one was the base catalyzed, and then one was the hydronium one. But I remember the hydronium one, it was the one that gave me the 1,2-diol. So this one has to be specifically hydronium. So this was an acid catalyzed ring opening of an epoxide. Oh, but look, right over here I have an epoxide. This was the second one that we did. So we did the acid catalyzed, then we did a binary acid one, right? And we remember that one, it put an OH on this side. I'm sorry, this is a good one actually. Look at this, that carbon's a secondary carbon. That would be a primary carbon. If you imagine them as their carbocation, that would be a primary carbocation. That would be a secondary carbocation. This is really, really a tricky one, right? Because we would protonate this oxygen with the hydrogen, and then the chlorine would have to come and attack one of these carbons. That's a primary. That's a secondary. Do you remember the rule? Chlorine prefers tertiary, then he prefers primary, then he prefers secondary. So which one would he have preferred? Primary here. So then what would be the result here? You would have your Cl going at that carbon there, and then you would produce a alcohol right there. Okay? So that's that reaction. All right, let's come over here to this one. PBr3. Okay, so now we got to guess the reactant. Well, I gave you PBr3 and gave you pyridine. All right, and I gave you the product. Well, I remember PBr3 was a substitution reaction of an alcohol. So I start with an alcohol. So I had to start with the alcohol, and then what did I have to do? I had to replace it with a bromine. Oh, well then what I do? Just draw an alcohol there. That's it. That was a pretty easy one, right? Cl, and then I'll have an alcohol there, and then I'll have a Cl here. If I would have had the stereochemistry, for example, if this one was on a wedge, this one would have been on a dash, but I didn't do that in that one. But it would have been if I would have left that there. Okay. Now, next one. I'm looking at this guy, and I see a hydroxyquinone. And I remember when we did the hydroxyquinone mechanism, I did it with the this reagent right here, right? Our Fermi salt, right? And we did it with UV light. And then what happens here? What it does is it oxidizes these hydrogens, converts them into radicals, and then after that rearranges to form a parabenzoquinone. So what do I get out of this? I get this structure right here. Double bonds here on the side, double bond oxygen to get me my p-benzoquinone. Okay? Then, if I do this reaction here, I have an ether. We did this reaction. We did the ether, and we had the hydrogen here. What happens? The hydrogen actually gets added onto the oxygen, so we protonate this ether. Then what? Remember that this bromine? What's he going to prefer? He's like, I like the way that guy looks. So he's going to come and he's going to attack that carbon. So if you remember that, it breaks this up into an alcohol and into an alkyl halide. So what do we get? This side right here will become the alcohol. This side right there will become the alkyl halide. So what do we have here? We have, boom, boom, there's our alcohol right there. And let's get this carbon up there. And then this little 2-carbon structure right there, 1, 2. That's our ethyl group there, but we're going to have a bromine there. So we have bromoethane there, and then we have 2-butanol there. So that's our product there. So let's put add symbol there to show that they're 2 distinct products. All right, then we have this one. Okay, well we got a benzene ring that's acting as a substituent, so it's a phenyl group, and then we got 1, 2, so it's a 2-phenyl, ethanol, right? We got this alcohol. Then I turn this alcohol into a double bond. Well, I know that there was 2 reactions of an alcohol. One had to be tertiary, and we already did that one. That one was the H3O+, and that's the only one that has to be tertiary. So if it has to be secondary or primary, that has to be POCl3. So if you remember that one has to be POCl3, right? If you remember that reaction, then you run it with a pyridine because the pyridine helps to be able to pull the hydrogens off of that OH whenever you form the OH+, whenever you're doing the OH is attacking the phosphorus from the mechanism. All right, now I look over here. I got chloro-trimethylsilane, and I'm protecting the alcohol. Oh, well, I just kind of gave you the answer then. So this had to previously be a alcohol. So this would be a alcohol right here. So just get rid of the trimethylsilane right there, and then just put a alcohol there. So boom, 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 and then the alcohol. So that's a protecting reaction. Let's keep going. Now we have to take into consideration stereochemistry. So we have SOCl2 and pyridine. Well, if you remember this reaction, it's a substitution reaction. We're taking the OH and we're going to be replacing it with a chlorine. But if you remember, this was that funky reaction, right? Where generally when OH leaves, Cl can attack from the front or the back, which it could create a racemic mixture with inverted stereocenters or retained stereocenters. In this case, all of it goes into the retained stereocenter, or almost most of it does. So what we say here in this case is that this guy will get substituted with a chlorine, but the stereocenter will be retained. There will not be an inversion of the stereocenter. All right. Then we have 250 degrees Celsius. That sounded like that was that one reaction where I started off with this benzene with that whole ether group over there. That's that Claisen rearrangement. And I don't know if I mentioned it in the mechanisms, but remember, you have to heat this up to some pretty high temperatures. You got to heat this up to 250 degrees Celsius so that you can start getting these electrons moving, so that pi bond that we had up here before would come and attack that carbon. So if you remember, all I have to do is I have to imagine this whole group right here. So this guy right there used to be right there next to the oxygen. And then this guy here used to be all the way at the end. So let's just go ahead and redraw this then. I'm going to have my benzene ring here, and I'm going to have my oxygen. I'm going to get rid of that hydrogen. It's going to come back over there. Then what? I'm just going to draw this in order because I remember at one point in time, this thing right here used to be where? All the way over there. And this point right here used to be right there. So now what happens is if we come backwards, we can kind of imagine how it would have looked like. We'll have CH2, 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 how many are there? 1, 2, 3, 4, 5. So CH2, 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 CH, double bond, CH2. And how would I have been able to envision that? Remember, this guy comes and attacks there, and this breaks off and forms a double bond right there. So that's why this piece will look like this piece, and this end right here would be that guy right there, okay? So that's our Claisian rearrangement. Then we got PCC, pyridinium chlorochromate. He loves to be able to oxidize alcohols, primary into specifically aldehydes, secondaries into ketones. Oh, this is a tertiary. Tertiary alcohols, remember we said, PCC can't react with tertiary alcohols because there's no hydrogen to be able to remove here. So if there's no hydrogen that I can remove, this is a no reaction here. A little bit of a tricky one right there. All right, now we got an aldehyde here. And we said that aldehydes, if I react this with 3 of the possible reagents, sodium dichromate, this guy CrO3 with acid, or if I react them with chromic acid, H2CrO4, I can oxidize an aldehyde even further and all the way into a carboxylic acid. So I could turn this guy all the way into a carboxylic acid. Okay. Last one, and then we're going to go into the multi-steppers. All right, so you see OH, you see OTS. Remember, I could have just as easily drawn something else. I don't have to put OTS. Remember, TS was that tosyl group. Remember that? And then when it's binding with the oxygen, it's a tosylate ester. So I could have easily have just done this too. Remember that. Sometimes it's just easier to abbreviate things, right? But I could have just as easily drawn that right there, where that oxygen is that guy right there. So that's our tosylate ester. So I remember tosylate esters, these were good leaving groups. So what did I have to add here? I had to add a tosyl chloride. So I had to add, we can actually draw this whole molecule if you want. We'll just do that anyway. Or you could have put TSCl, which is tosyl chloride. There's the methyl, there's our sulfur, double bond oxygen, Cl. And this is a good leaving group, which could allow for certain types of substitution or elimination reactions. Okay, so that covers pretty much all of our single-step reactions. So that was a bunch of them, just to get a hang of doing some practice problems so that we can put what we learned into action. Now it's going to go, these guys are going to be some hard ones, okay? These are multi-step reactions or synthesis reactions. So in other words, we have to start with a reactant, and I'm going to give you the product, and you have to give me what I need to get all the way to that point. These are hard. And I made some of these kind of hard, I made some of them kind of easy so that we could have a good mix here. All right, so if you're able to do most of these, you're in good shape here. All right, so first thing, I look here and I see, what's the first thing I do? I have an epoxide. Then I look over here and I say, oh shoot, I got an ether with this cyclohexane ring. Oh wait, but that looks exactly the same there. I have a methyl there, so somehow, some way, I must have turned this into an alcohol of some form. Well, what could I do first to be able to get this guy into some form where maybe I had it into an alcohol? Because I don't have a halide, so it couldn't have been the HCl. I don't have an ether, so it couldn't have been some type of methoxide. Well, the only other thing I could react with an epoxide is the H3O+. That puts 2 diols on there. Let's try that then. So if I do this reaction and I react this first off, so I say the first thing I do is I use H3O+ and tetrahydrofuran, or just whatever I need to use here for this. And this is what I would get right here, right? I would open up the ring and I would have a OH, OH. Okay, so we're a little bit closer here. A little bit closer. What else could I do? All right, well, I could, I'm looking here and I'm seeing not too much, right? But I see an ether. I know that this guy right here, we didn't mess with him, but this guy I did. What if I turn this guy into a halide? I do a substitution reaction with a halide. So I add on, I could do this SOCl2 or I could do the PBr3 reaction here. And then if I do that, I turn him into some type of big alkyl halide chain, and then I could react it with an alcohol like this. Let's see if it works. And again, this is just trial and error. There could be multiple ways to do this one multi-step reaction. Let's try it this way though. And if you have a different way, leave it in the comment section of what you did. So what I'm going to do here is I'm just going to do the PBr3 and the pyridine. And the good thing about doing this reaction is PBr3 and pyridine, they don't work on tertiary alcohols. They only work on primary and secondary. So I'll leave that one alone. That's why I feel like this reaction is looking good so far. Okay, so it's going to convert this guy into a bromine. And again, if it was on the wedge, it would have inverted, but we're not going to care about that right now. Okay, now what can I do here? Well, then what I could do is, I don't want to like have my alcohol, because what I want to do is I want to try to treat this as though this is an alkyl halide and attach it onto a cyclohexanol. So in order for me to do that, I can't have this alcohol reacting. So guess what I'm going to do? I'm going to protect the alcohol. So in order for me to protect the alcohol, if you remember, that means reacting with the chloro-trimethylsilane. And what does that do? It protects the alcohol and prevents the alcohol from reacting. So now I have this O, TMS. Cool. Now I have this alkyl halide that I can go ahead and add. So now I'm going to try to do what? I'm going to try to do a Williamson ether synthesis. I'm going to try to treat this guy as my halide because I protected that alcohol. And then I'm going to react with it a cyclohexanol. So now what am I going to do? This is my alkyl halide, and I'm going to react this with cyclohexanol, right? So I'm going to have here my cyclohexanol, and then I'm going to take this cyclohexanol, and I'm going to treat him with sodium hydride. If I treat him with sodium hydride, what does that do? That gets rid of the hydrogen, and then I'm going to add on this Br there. And look what this gives me. This gives me, so I'm going to actually put in here, I'm going to put sodium hydride for this. And look what this gives me here. So now I'm going to add this to this point here. So I'm going to have boom, 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 boom. And then I'm going to have oxygen right there, bound with the bromine. But the bromine is actually going to leave, and we're going to attach it on right there. So let's go ahead and draw it like this. And again, what would be adjacent to that point right there? You'd have this methyl group and this OTMS group. Looking good so far. What else could I do? Now I just got to get rid of the TMS group, and then I'm at my product now. How do I do that? If you remember, we just add some hydrochloric acid. And we finished our product. So this is probably as hard as it's going to get, guys. All right, this is a pretty intense one. If you didn't get this one, don't be mad about that. This is a really intense one. For those of you who did get it, awesome, good job. So again, this is a 1, 2, 3, 4, 5 multi-step reaction. So that's a pretty intense one. All right, let's go on to the next one. Okay. So I look here at this guy. I see I have an ether, and then I see over here I have an alcohol, okay? So, what can I do here? Well, I noticed that I have this little ethane group with the iodine. Well, I remember the only reaction I could do that is when I reacted an ether with some type of binary acid, specifically HI here. So let's do that. Let's give it a shot. So if I do the first thing, I react this guy with HI, hydroiodic acid. Naturally, the iodine will attach to that carbon right there, and this guy will become an alcohol. That's looking good. Let's go ahead and see if that works. So boom, 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 right there, right? Put my alcohol there, and then the other product from this is going to be the iodine. All right, this is looking good so far. But wait, how the heck did I get an iodine there? Let me see here. What could I do now? Okay. Well, the only other thing I could do, thinking about it, is if I try to make a double bond. If I try to make the double bond, I could then try to convert that into an epoxide. And then if I convert that into an epoxide, maybe then I could do the binary acid reaction. Let's see if that follows. So let's say first off, I go ahead and I react this with POCl3 and the pyridine. If I do that, if you remember, it takes the hydrogen from the nearby carbon who has less hydrogen. So there's 3 there, 1 there. I'm going to take it from there, right? Then what do I get here? OH, and it's going to actually leave, right? So actually, you're going to actually do what? You're going to remove the OH here, form a double bond, and you're still going to have that iodine structure right there, that iodoethane, but we're not going to worry about that right now. We'll pick them back up afterwards. Okay. Then what can I do? Let's go ahead and react this with an epoxide. Let's do the epoxide formation. So how do we get an epoxide from an alkene? A peroxy acid. So now let's react this with a peroxy acid. If I react this with a peroxy acid, it's going to put a peroxy acid like this now. Okay, so what would this result in? If I reacted this with HI Again, remember, O will pull the hydrogen. When he does that, you'll have that little positive charge on the oxygen. The iodine will come in and attack that carbon right there, and what do you get? You get this product. Okay? So that's that one. So how many steps is this one? This one was also kind of a tough one. So 1 step, and then over here we have 2nd step, and over here we have 3 steps and 4 steps. So this is a 4-stepper, so it was a kind of a tough one too. All right, let's do another one. And again, you can have multiple answers. Leave your answer down in the comment section too, okay? So I'd like to be able to see what you guys got also. All right, so let's do this one right here. So let's go ahead and start this one, and let's see here. I'm looking at this and I see an alcohol, and I see my alcohol hasn't changed. Possibly, if that's even the same alcohol, right? And again, this is just a guessing game. What I'm gonna try to do in this one is I'm gonna try to protect my alcohol. I'm going to protect my alcohol so that if I protect my alcohol, I don't have any side reactions. Because what it's looking like happened here from my hypothesis is I left this OH alone. I didn't mess with it the whole time. Then it looks like I did something with this where I turned this into an alcohol and then into an ether, and then I oxidize that alcohol. So I want to protect my alcohol and make sure that it doesn't react. So what I'm going to try to do here first off is I'm going to try to go ahead and do... Let's go ahead and do, first off, let's do a TMS reaction. So let's do a TMS. So let's do the TMS-Cl. So our chloro-trimethylsilane, and let's protect that alcohol so we don't have that alcohol reacting. So now we have this O-TMS group here, and we have our epoxide. Okay, let's go ahead and open up the epoxide, but let's open up the epoxide to where I put an OH here and an OCH3 here. Well, that's fine. I can do that because the OCH3, it could actually attack from either side because they're both secondary, so it has no preference. So I'm going to do that. I'm going to go ahead and do a reaction where I start off and I do this with CH3, O negative, and I react this with its conjugate acid. And when I do this reaction, I get this. O-TMS, so I'm still protecting my alcohol. And then what I'm going to do is I'm going to try to follow over here, OCH3, and then alcohol popping up here. Okay, well this is a good thing that I protected my alcohol, because if I would have tried to do this reaction first off, I would have had 2 alcohols. So now I don't. Now I only have 1 alcohol. So I'm going to keep this the way it is for right now, and I'm going to keep that alcohol protected. I'm not going to remove it yet. So now what I'm going to do is I'm going to go ahead and oxidize that alcohol right there and turn it into a ketone. So what did I need to use for that? Pyridinium chlorochromate, PCC, and pyridine. And then what does that give me? Puts the OTMS still there, still protected, and then we still have that ether group over there, and then we have our ketone. And then what am I going to do now? Now I'm just going to get rid of the TMS. So if I get rid of the TMS now, all I'm going to do is put it in some hydrochloric acid, and I'm going to remove that OTMS group and convert it back into an alcohol. Okay, so how many steps was this one? This one was 1, 2, 3, 4-step reaction. So again, pretty tough one. All right, so let's look at this last one here. This last one here, we're starting off with some type of benzene ring here with a whole long ether chain here, right? It's got a whole bunch of hydrocarbons here with a double bond. Well, the only reaction I can do with this at all, right away, I know right away, the only thing I can do with this is I can heat it up. So that's at least one thing I know I can do right away, is I can heat this up, because there's no other reaction that I know that could mess with this frickin' thing. So I'm going to heat this sucker up and then give me my normal product from this. So this would be a good thing for a single-step reaction if you remember that one that we did. What are we going to get? We're going to have a OH here, and then remember, all of this side will attach right here. So 1, 2, 3, 4. So let's write that down first. So 1, 2, 3, 4. And then after that we have, so 1, 2, 3, 4. This has to be a CH, double bond, CH2, because we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, we're good. So now I did that. Okay, what else could I do? Well, there's not as much I could do here, so I'm trying to look. Let me see here. I could take this double bond and I could try to turn this double bond into an epoxide. Let me try this. Let's try to take this double bond right here and let's try to turn this into an epoxide. Because the only reason I'm saying that is, okay, here's why. Here's my reasoning. I'm looking at this whole thing right here. And I notice the double bond's gone right here. And somehow, some way, I added on an ether. Well, the only way I know I can get, I'm sorry, not an epoxide. The only way I know that I could get a double bond to an ether, not an epoxide, I'm sorry about that, is I react it with mercuric acetate. And I have to do it with a CH3OH. So what am I going to do here? I'm going to react this with mercuric acetate here. And then I'm going to react this with CH3OH. And then remember, to remove the HgOAC, I do this with sodium borohydride. Well, what's the result of that? I have CH2, 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 C. Remember what happens? This is going to turn this guy right here. What's going to happen? Whenever I do this reaction, I get a CH3 here, and I get my ether right there. And then what else do I have? I have an OH there. And we still have our benzene ring. Okay, what else can I do here? All right, so I got that part. That's good. Let's finish this off. I went from an OH to an ether. Williamson ether synthesis. So if I got to do Williamson ether synthesis, I already know that because that's how I get an alcohol to an ether. So what do I need to do for my Williamson ether synthesis? Add on this whole thing here with the halide at the end. So I need to add on what? First thing I got to do is I got to deprotonate it, so I got to add on sodium hydride to get rid of that hydrogen. Then I'm going to add on a BrCH2. How many carbons do we have? 1, 2, 3. Let's do that first. 1, 2, 3. CH, CH3, O, CH3. So this was a tough one too. So again, how many steps was this? One step, starting with the Claisen rearrangement, heating it up. Second step was turning this alkene into an ether. Sorry about that again. It was going from an alkene to an ether. Before I said an epoxide, I'm sorry about that. Okay, so we're turning it into a ether. Then after we turn that into an ether, then what do? Then we do a Williamson ether synthesis to get our product. So this was 1, 2, 3 steps. All right, guys, so we did do a lot of stuff in this video. We did a lot of practice problems. We did a lot of single-step reactions. We did 4 multi-step reactions that were very, very difficult. So if you didn't get all of these, it's okay. But again, leave your, maybe you got something different from me. Leave it in the comment section. I'd be interested to hear what you got. All right, Ninja Nerds, I hope you guys enjoyed this video on alcohols, ethers, and epoxides.